thanks. Well, my name is Gonzalo. I'm Apache Pinot committer and also been hired by Star3 Inc. One thing I noticed in the previous talks is that I didn't have time. As you can see, my English is not the best. And I didn't have time to write all the questions I would like to write. So I included this QR here. I have to say that there are almost as many slides as QRs. So you are going to, I mean, if you have your mobile phone, it's going to be useful if you want to do that. One of the things I included also is the link to the slides themselves, so you can just use that. You don't need to ask for that in the questions. Yeah, I'm going to talk about how Apache Pinot works, executes queries, but this is not something specifically to Pinot. It's something we could be using in any database, distributed database, and the main theme actually is this sentence, which is an axiom for me, but I mean, we can discuss about that, but usually databases, the performance in databases is limited by I/O, okay? Just given its network, disk usually, even you can consider the memory, your I/O, right? And this is the case for Apache Pinot, okay? I wanted to introduce Apache Pinot as fast as I can, because I assume, I mean, how many of you have been, I mean, how many of you know I mean, having heard about Pinot, for example? Okay, a bunch of you, but the vast majority did not. So I wanted to talk a little bit about Pinot before. Apache Pinot is an open source database, okay? Whenever you hear something is Apache whatever, it's an open source. Apache is an open source foundation that under that umbrella there are several open source projects, and one of the key points of the Apache Foundation is that it owns the legal trademarks. But usually it's not Apache Foundation is not the one that paid for the contributors. There are different companies that contribute, or there are different individual contributors that contribute to the software, but they are being paid by their own companies. Okay, and one of the things that the Apache Foundation tries to enforce is that there has to be different companies paying for these contributors to avoid this kind of situation in open source where you have, yeah, this is open source, but there is only one company paying for that, so they are the one that control what is going to be published in the next release and stuff, right? And well, it's you know, there are a bunch of words there. It's an open source, real time, low latency, blah 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 blah. But the two parts that I think, or I really like to talk about, is that it's a SQL but not relational database, which sounds like mind-blowing for someone. And it's also written in Java. As I have said before, I'm a Java developer, and I firmly believe that you can write very fast code in Java. Java is not like 20, 30 years old. I mean, it's 30 years old, in fact, but the Java we write right now is quite better in terms of especially performance, but lately it's also improving the quality of life for the developers. So it's not the same thing we had like 20 years ago, okay? This is the last slide I'm going to be talking about Pinot in a not technical way. Pinot has been created in LinkedIn, this guy. But it's been used in different places. And these are just numbers. You know, when I'm old enough to remember that horrible marketing post from MongoDB, where they say there were a big data ready database, and they were talking that they were able to ingest like 1 gigabyte of data or something like that. It was like very embarrassing. But people using Pinot actually have like very large numbers, okay? These are, again, these are not, I told you that I've been paid by Star3. These are not Star3 customers. They are companies that are using either open source Pinot or their own forks with their own proprietary extensions, okay? In Star3, we also provide, we are one of the main contributors of Apache Pinot, but we also provide some database as a service, so you can pay us so we can manage all the cloud infrastructure and stuff, and you can just use the database as a user. So great. So let's talk literally about Pinot itself, right? So Pinot is as I say, SQL database. The key point, the entry point here is the table. You run queries and ingest data into tables. These tables are divided into different segments. The segments are disjoint. They are a list of rows that are disjoint. Different segments are disjoint, and there is no row in common between them. And these segments are formed by stored in a columnar fashion. And these columns are formed by indexes. It's a little bit strange, but we have some customers. It's a super niche thing, but we have some customers that have indexes over data they don't store. So it's super strange, but it's something you can do. We can discuss about that if you want in the queries in the question time. These segments they are stored in servers, and these servers, a single segment may be stored in different servers, so you may have high availability. And then we use brokers to query these servers for some information, right? And the ingestion, I'm not an expert in the ingestion side, and I don't want to spend too much time here, but I think it's important for all of you that don't know Pinot to know that this is not like a Postgres database or a Mongo I mentioned before, where you were inserting data, updating data, removing data in an OLTP fashion. Here, instead, we ingest data from there are like two main different ways to ingest data. One is batch ingestion, where you push some Parquet file, some huge CSV, whatever, and we create segments with that, and then you can use them. But the most common use case is to ingest from a real-time source, usually Kafka. As I said, it was created in Pinot, and in LinkedIn, and LinkedIn were also the creators of Kafka, so they were using that together, and they are still using that together. The majority of our customers, they are ingesting data, for example, from Kafka. And one funny thing we can do, and very important later, is that you know that in Kafka and other like Kinesis and stuff, you can define different partitions, and you can configure your tables to use that partition information, so you can do several optimizations later. We support like upserts, different storage, a lot of different things. I mean, there are other talks about Pinot online. In fact, we had a conference running at the same time this one, an online conference, RTA Summit. You can look for it, and all videos are going to be available soon. So finally, let's start with the query side. Okay? In Pinot, we support 2/3 different query engines. We have the single-stage query engine, which is the one I'm going to talk about now. It is the first one we created. I think it was originally created in LinkedIn. And then we have the multi-stage query engine. I'm going to talk about that later. And we are right now working on some time-based query engine for time series. And focusing on single stage, it's a pretty simple, very fast engine that is focused on reducing disk usage. Okay? But the same side is very limited in terms of the SQL you can execute. In order to be fast, we do different tricks, right? One of them is to prune segments. We try to say, okay, we know for sure that this query is not the data you are looking for is not going to be in this segment, so we are not going to even open them. The good thing is I don't have to talk about that, because yesterday we had a talk about that. So you can, I hope you were able to be there, and in case you don't, you can just watch the video later. Another optimization we have is the approximate aggregate functions. Sometimes you really need to have an exact value for your queries, but in some other cases, you don't need that, right? So we support different approximates, different ways to optimize that. And it's not something that only we support. It's something super well known. This video, like here, I watched it this morning, and it was very funny. I was looking for some image to place there, and I think it's very funny. This is the QR to access that video. Don't do that, please. Don't do that now. But for example, the hyperlog is being used to calculate an approximate number of different values in a very large data set. The TDS, for example, is being used to calculate percentiles, right? You have to calculate a percentile. The normal thing you have to do is to store that in, let's say, an array, order that, and look for the P50, P99, whatever you want, right? With TDS, you can do that in a easier, cheaper way to calculate that, but with a control-related error. So maybe it's not the exact value, but it's going to be close, right? And finally, we have tons and tons and tons of different indexes and ways to store your data. Okay, we have inverted indexes, which are pretty classic in normal databases, right? We have range indexes, which are pretty cool. As far as I know, there is not much. I mean, there is no video about them, but there are some blog posts, interesting blog posts online. And we have JSON indexes, we have Lucene indexes, and we also have starter indexes, which are the ones that gave name to the company I'm working for. This talk here, it's a talk in the CMU, which is, they have amazing videos related to databases if you want to watch them. All videos are great, everything is published, so and free to consume. So feel free to do that, to take a look if you really want it. During pandemic, there were some special sessions, and the CEO of Startree was there explaining specifically the Startree indexes. So if you want to take a look, they are very interesting because they are some kind of, they are not a materialized view, but there's something like that. Let's imagine that you want to query something like this, like aggregate the average of some value, right? You can use these indexes. I'm not going to talk about that, but I think it was useful. You can use these indexes to, usually you have to execute this aggregate. You have to read all the data, maybe use some index to filter some rows, but you have to read a lot of data, a lot of rows, to calculate the value. With this thing, automatically the query engine is able to, you create this index, the query engine is able to say, okay, we have this starter index. We can use that to return the actual value for each segment. And then we can reduce I/O by several orders of magnitude. As I said, take a look at the video, is great. But let's talk about the actual planning. Okay, let's assume that we have a customer running this query. This query is sent by the customer. It arrives to the planner. It arrives as a text, plain text, right? And the planner optimizes it a little bit, and parses and optimizes it a little bit. And then we go to a phase where we prune different segments. We apply different pruners, right? For example, let's say that here we are looking for value X, and for whatever reason, either Bloom filters, mean values, whatever, the pruner knows that it is for sure that the value is not in segment 4. Sorry, I didn't say that, but let's say that we have 3 servers. These red boxes are the different segments for table A. Okay, so let's say that the pruner knows for sure that the data is not going to be in this segment 4. Okay. Then we have the router phase, and then we said, okay, fine. So we know that we need to use segments A1, A2, and A3 to read, to get the actual result, right? And as you can see, some of these segments are in different places, different servers. So, okay, so you can, the router is the one that decides which ones are we going to use, and it basically calculates a pair of server and list of segments that has to be used. Okay, and then is where the data starts to go flow in the other direction, right? The thing we do is that each server that has a segment, at least one segment assigned, calculates the local value. In this case, we are calculating an average, and we don't calculate the actual. The local aggregate is not the average, but the sum and the count. So we can then re-aggregate that. And then the thing we do is to move that information to the broker, and then calculate the final result and send it to the customer. As you can imagine, when you are, let's say that you are reading, I don't know, whatever number of million of rows. That's my phone. Sorry. You know, Amazon always calls in the worst moment. Yeah, sorry. It's literally Amazon. I was saying, yeah, let's imagine that in your segments, you have tens of millions of rows, right? Usually when you aggregate and group them by some key, the number of rows are going to be reduced by a lot, right? So the number of rows that are moved from each server to the broker, when you have an aggregate on group by, is orders and several orders of magnitude smaller than the original data, right? And this is what, I mean, this is a key point of this for this system to work, okay? So, just last, another extra thing. As I told you before, there are several options, several ways we could split segments between servers, right? This is the one I showed you before, but the broker may have decided to, instead of using server 3 to execute the read A2, it could use server 1, right? Why? I mean, obviously, if you do that, the parallelism is going to be worse. You're going to have less resources applied to your query. But that's something customers sometimes they want to do because you have to think that we don't have a single query running at the same time. We have multiple queries. So usually it's better to have your machines focus on something instead of having to all different queries competing for different resources. And that's some kind of, you can tune Pinot to use one or the other mode, right? Yeah. As I was saying, there are some limitations of this model. If we want to execute a join, we don't support joins in single-stage query engine. And the reason we don't do that is because in order to execute a join in a trivial way, the thing you will need to do is to, I mean, let's say that you have the data split in this way. So we have, again, table A, but we have also table B, and we have 2 segments in table B. If you run the join, you cannot, there is no way to run a local join here, because maybe some row in A3 has to be merged or joined with a row in B2, right? So actually, in the abstract, the thing you need to do is to move all your data from B2 somewhere, then move your data from A1 somewhere, then calculate the actual result, the actual join, and then send it to the client. In Pinot, following the normal scatter and gather way to work, we will do that in the broker, right? And the problem here is, I mean, it's pretty obvious, right? We have to move all the data, and we have to copy, to keep in memory a lot of data, right? It doesn't make any sense, and as far as I know, almost nobody implements joins that way when you have to deal with a large amount of data. That's why we created, one of the reasons why we created the multi-stage query engine. In the multi-stage query engine, I think I moved this a little bit, okay. We have a full SQL support, and the thing we do here is to create a tree of different stages, and each stage is actually, it can either be, I mean, we create a tree, right? And the leaves of the tree are single stage query engine phases, and the other parts are what we call intermediate stages, where we do all the kind of magic we can do to improve the performance of these joins, okay? And that's why we can use all the techniques we use in single stage, but we use them in the leaf stages. We don't care too much about them in the multi-stage. And therefore, in this part, we are going to focus more on the network access, okay? Yeah, I was saying, how we implement joins then in multi-stage query engine, right? There are several ways. This is probably the most general one, which is to apply broadcast and random partition in some of the columns. Let's say that we want to execute this query, right? And the thing we're going to do is to say, okay, let's create some virtual partitions so we can keep the information on different servers, and we can actually execute some kind of partial join, okay? The idea is we have to think how to do that, but the idea is to apply the same thing we apply in the other case, for the aggregates, right? Let's have partial join somewhere, and then calculate the final one. I forgot to add an arrow here, but again, whatever. So this is one of the ways, okay? Broadcast plus random. In this way, the thing we do is to say, okay, let's assume that the thing we're going to do is to copy table B in all the servers, and then, which has a even higher cost than before, because we have to copy table B in all the servers. So the more servers we use, the more copies we need to execute or to send. Okay. And then what we are going to do is to say, okay, but we don't need to copy all rows of table A in all servers. The thing we are going to do is to apply a hash on this value, okay? Whatever hash function we use. And then we're going to store here or move here all the values, all the rows whose call 1 is equal, module 0, module 1, module 3, sorry, is equal to 0. Same for the other one, changing obviously the equal to 1, equal to 2, okay? If we do that, the number of rows we send is still proportional to the number of rows we have in the original tables. But the memory we have to store, it's quite smaller, because we still need to keep a copy of table B in all the servers, but we only need a partition of one of these partitions, which is if we have 3, we are going to need only 1/3 of the data on each server. Okay, this is not great, but it's the only way we have to evaluate this kind of joins. Okay, but most of the joins are not like that. Most of the joins you have in written probably are equality joins. You join by equality, right? In these joins, we can do the same trick, but better, because we can partition by table A as we did, but we can also say, OK, let's apply a hash on the other one. So we know for sure that if, I don't know, the value, the hash is a function, obviously, that produces a deterministic value. So if the value of this module 3 is going to be 0, the hash applied to this other side, module 3, is going to be 0 as well. So we know for sure that any two rows that can be joined, they have to be in the same server, so we don't have to care about different combinations, right? And if we do that, the good thing is that the memory is also reduced. Good. And almost finally, as I told you before, we can use partition and ingestion time, right? So we can if you craft your use case for some specific query, let's say that you have one of the main usages is to join by customer ID. Okay. Can you hear me? Okay. So you can prepare your Kafka topics or whatever to partition by that customer ID, and therefore we can be sure that we are storing partitions also on disk, right? So if you are executing that specific query, I changed the names a little bit here to indicate the number of the partition. Okay, if you are doing that, the thing we can do automatically is to say, hey, you are executing the same join, but in this case, you are doing that for the using equality on the partition key. So the thing we're going to do is to use the same servers you already have, right? If we do that, the memory we have to consume is the same, but the network is completely 0 because we don't need to move any data, right? This is super cool, but it's very restrictive. It depends on the ingestion. So if you want to do that by 2 different columns, you cannot do that. You can only partition by 1. I mean, you can execute a join saying customer ID and country, for example. Both of them has to be equal, blah, blah, blah. But you cannot say, OK, in one query, I'm going to partition by customer ID, and the other, I'm going to partition by country. Okay. I mean, you can do that, but you will need to create 2 different tables and copy the information. It's very expensive. And the other issue you could say is that, as you can see here, we have only 2 servers running because the parallelism is limited by the number of partitions you have. Okay, if you have 10 servers, but only 2 partitions, well, it's not gonna. You are only going to be able to use 2 servers anyway. Side note, in Kafka, please. I know that there are tons of post around saying, hey, please don't use thousands of topics in Kafka, but you don't have to use 3. You can use 30, 300. It's going to be fine. Okay? And it's usually better because you are not going to need to repartition your information later. And how much time do I have? Like 4 minutes? OK. So let me do final talk you about explain you a final optimization. This is a little bit strange, but it's super cool. And not so many databases support it. All the things I'm saying are things that is not something that only Pinot support, but I think it's cool. But the pipeline breaker is something that, again, some other databases support, but it's pretty cool. And the idea here is to split the optimize and execution phase and have several of them for the same query. I'm going to show you an example. Let's say that we have this large table, and we are joining that with another table, which is not that large. And we're just joining them in an equality way, right? So this can be represented as a tree in this way. Okay, we are projecting some rows, or if we are reading in the other direction, we are scanning the large table, we are scanning the other table, then we are sending the information somewhere to execute a join, and then we are projecting some columns. Okay, this specific case on this specific query, it's equal to this one. It's semantically equal to this thing. Okay. I'm tricking you a little bit, but it's not exactly the same thing, but I'm going to talk about that later. It's exactly the same thing, because I am not projecting data, well, that slice is incorrect. But I'm not projecting data from table 2. I'm only projecting data from the large table. Okay? This is OK, but the cost is going to be the same. The cool thing here is that when you apply pipeline breakers, the thing we do is to say, hey, OK, cool, you're going to execute that. Then the thing I'm going to do is to first execute this part, OK? This read from table 2, which is not as large as the other. Sorry. So I'm going to read from that further, OK? And then I'm going to change the node I have here. I'm going to change that with the literal result that query returned. Let's say that it was 1, 2, and 3. OK? If I have that, this is suddenly not a multi-stage query. We only have one single table participating in this query, right? So this can be transformed into this. Instead of scanning my whole table, the thing I can do is to use my indexes to only read the rows that actually matter, right? This is cool, and you can do that in your application. You can send first one query, get the result, and then send the second one. But it's cooler if the engine does that for you automatically, right? You don't have to care about anything. It's automatically done. The only problem is that you cannot always do that trick. The trick can only be done if you are using inner joins, if the columns of one of the sides are not projected, and also, which is the trickiest part, semantically, SQL is very complex. Okay? You can assume that both things are the same, but these two things are the same, but they are not, because in a join, if there are multiple columns in table 2 whose value is equal to this one, there are going to be one row. One row is going to be produced for every match, right? But that's not usually what you want. Usually you want to say, OK, give me the address of that other place or whatever. And you know that the other side is unique by the key you are using, right? But the query engine doesn't know that, because in all app databases, usually there's no concept of unique, because it's super expensive to keep. So sometimes in Pinot, at least, it's cheaper to run something like this, where you write, hey, give me the distinct values of that table, instead of give me just the values. Because first of all, distinct values can be calculated pretty fast with dictionaries, but also because if you do that, the engine can be sure that it can apply this transformation. We provide some hints, so you don't have to do that, but usually it's better to not use the hints. Okay? And I think that's most of it. I have some extra slides, but I'm not going to have time. The extra slide with some extra advanced things are hidden in the slides, so if you want to use them. Obviously, we are an open source database. We are open for contributions. This QR send you to the beginner task if you want to join us. And well, yeah, 2 more QRs, the slides, as I said, if you want to take a picture. And yeah, finally, this is like a raffle we offer in Star3. This is our mascot. It's super cute. I have one of them is super cute. So, and that's it. Thank you for your time, and I think we have time for some questions before lunch.